All right, grade 11's intermolecular forces is the follow-on extension of atomic combinations. I know we're yet to just do some revision on it, but I thought let's just teach everything finished completely, close the chapter, and then we can have a look at some questions based on exam and test level, and see how well we fare with those questions, get our brains wired and warmed up for it. So I thought maybe let's just kill everything off one time, and then we can obviously focus just on revision when we wrap up the topic. Okay, so I just want to introduce intermolecular forces and what it is all about. Okay, so intermolecular forces, okay, they are forces that obviously exist in between atoms in compounds and molecules. Okay, but more specifically, intermolecular forces are attractive forces between molecules or between molecules and ions. Okay, so you can have an ion bonded molecule, or you could just have a molecule. Okay, so important thing that we need to understand about intermolecular forces is the fact that they are attractive forces. Okay, they are attractive forces, very similarly to that of a magnet. Okay. Now, the forces that exist between the molecules, they will determine, okay, whether the object is, of course, a solid, liquid, or a gas. Okay? The forces will determine what state of matter, all right, it is at any or at a given temperature or at any given temperature. Okay, the type of intermolecular force will determine the state of matter. Okay, melting points and boiling points of substances, they serve as a measure of the strength of the force of attraction. Okay, so we're going to be having a look at those melting points and those boiling points. Okay, I'm just going to add them to our list of what we're going to look at. Okay, melting points, okay, as well as boiling points. Okay, we look at that at these two things because they measure the strength of the forces. So obviously, the higher the boiling point means the more kinetic energy is needed to overcome those forces to break them apart, just by example. Okay, of these forces. Okay, these are good notes to obviously take down to gear our brains to understand it. Okay, great. Substances with low melting points and boiling points, for examples, are held together with weak intermolecular forces, but the higher melting points and higher boiling points obviously proves true what I just said a moment ago, that especially with boiling point, if the boiling point is very high, of course, there's very strong intermolecular forces there because you need now more energy. We need to increase the temperature so we can have more energy to break those bonds apart. For example, 100 degrees Celsius is quite warm. If you don't believe me, dip your hands into boiling water and see how well you do. Okay? 100 degrees Celsius is quite warm. So understand, water, all right, water, which doesn't seem as a very strong substance. It seems very flimsy. We drink it every day, very healthy, very nice, very cool, and whatever. But boil water. Water only boils at 100 degrees Celsius. In other words, the phase or state of matter only starts to change at 100 degrees Celsius. So all the way leading up to room temperature, or whatever temperature it is when it enters the cold kettle, okay, all the way through up to 100 degrees Celsius, or just before 100 degrees Celsius, it remains liquid water. And when it is boiling, of course, we notice the phase change of liquid into gas or water vapor, right? We see the kettle start to boil. We see what we colloquially call as steam, all right, start to exit or start to rise out of the kettle as well, showing that, of course, water, which was liquid, is now being converted into water vapor or gas. Okay, so water's got fairly strong intermolecular forces keeping it together. All right, and we'll see why in just a moment. Okay. Forces between ions and polar molecules is the next thing I'd like to touch on. Okay, I'm just going to write my heading here quickly. Okay, got it. So when a positive or negative ions, okay, they come into contact with polar molecules. All right, when they come into contact with polar molecules, the negative side of the dipole will be attracted to the positive ions, and the positive side will be attracted to the negative ions. Okay, so if we draw it quickly, so what we do here, we got positive or negative ions if they come into contact with a polar molecule. So let's draw a polar molecule quickly. Okay, let's draw it like this. And I've got a positive side, I've got a negative side. Okay, so when ions come into contact with polar molecules, the negative side of the dipole will be attracted to the positive ions. All right, as well the positive will be attracted to the negative. So all the positive ions are going to come to this side of the molecule or dipole, and all the positive side of the dipole is going to attract all the negative ions. Okay, much like this. Okay, an example of this would be water. Of course, water is a polar molecule. Okay, if you didn't know that water is a polar molecule, which I'll write down for you, and we must never forget this. Okay, it's a polar molecule. Okay, so what happens here, if an ionic substance, okay, such as sodium chloride, okay, NaCl, let me just draw that L better because it looks like a big fat E, cursive L. Okay, this is an ionic substance. If water comes into contact with an ionic substance such as NaCl, okay, which is sodium chloride, and it's added to water, the positive side of the water molecules is going to attract, so the positive side is going to attract the C or the chlorine ions, Cl minus ions, while the negative side of water is going to attract the positive sodium ions, which is Na plus, and we've got Cl minus. Okay, so that's what happens in water when sodium chloride, which is known as what? Salt. Okay, so the positive sodium ions, they go to the negative side of water, because water obviously has a more negative side as well as a more positive side, and the negative Cl ions, the chlorine, gets attracted to the negative side of water. Okay, so it's called polarization or complete ionization in water. Okay, salt dissolves in water completely. Okay, it completely ionizes. In other words, all Na plus ions go to the negative side of water, and all Cl minus ions go to the positive side of the water molecules. Basically, what I'm trying to say is that it same exists like a magnet. Positive attracts negative. Okay, same way here, and negative attracts positive. Positive and positive do not attract, they repel each other, which I think is quite intuitive to understand and figure out. Okay, so this is forces that between ions and polar molecules. That's how it looks. Okay. All right, van der Waals forces. Okay, this is intermolecular forces, particularly those that do not involve ions. Okay, now any type of intermolecular force that does not involve ions is called van der Waals forces. Okay, now the first type of van der Waals forces that we can get is dipole to dipole forces. Okay, which I'll demonstrate in a jiffy. Okay, so when a polar molecule encounters another polar molecule, so let's draw a polar molecule again like we did previously. Okay, we don't have to give it a name or anything, just it has a positive side and has a negative side. Okay, when a polar molecule encounters another polar molecule of the same or different kind, of course the molecules will interact with each other. Okay, so let's draw another one. Okay, and I'll draw the positive or the negative this side and the positive on this side. Okay, cool. So we've got two polar molecules. Okay, cool. And they're going to interact with each other. Okay, and I'm just going to draw them in like a similar mind map form. Basically, I'm going to draw the result over here. Almost looks like I'm drawing a face. Okay, but the positive side of one molecule is attracted to the negative side of the other molecule. Okay, so we see I got my positive side here of this one, and my positive side there on this one, and I got my negative side here of this one and the negative side there of that one. So when they interact with each other, you just draw the one here, and then we draw the other one as well, just slightly underneath it like this. Okay, the first one's going to remain the same, the positive, the negative, and obviously the negative side of the other one is going to be attracted to the positive. Let me just change the color of that, sorry. Okay, and the positive side to the negative. So can we see, I'm just going to dot it out, what is actually going on here. Positive sides are attracted to the negative side, and the negative sides is attracted to the positive side, even if two polar molecules are coming into contact with each other. It's very similar to that of the ionic substances interacting with polar molecules. Okay, what is similar is that positive sides go to negative sides and negative sides go to positive sides. Okay, these interactions, however, decrease quite rapidly as the distance between the molecules do increase. Okay, and they are about 100 times more weaker than covalent bonds. Okay, so these dipole to dipole forces are about 100 times weaker than covalent bonds, which is a very important thing that we need to understand. As the distance increases between them, okay, what's going to happen is that the bonds are obviously going to get weaker. Forces of attraction that exist between molecules or substances in chemistry are quite dependent on the distance between them. Okay, if they're very far apart, the molecules are obviously very weak. The force of attraction are not that strong. But if they're quite tightly knit together, or quite tightly held together, then they have quite strong intermolecular forces. Okay. A special case of dipole to dipole forces, however, is hydrogen bonds. Now, hydrogen bonds, which we're going to get to in a jiffy, but I just want to introduce them here quickly. Hydrogen bonds are much stronger than other dipole to dipole forces. It's a type of van der Waals forces, but with the exception that it is quite strong, or in fact it's much stronger. Okay, and it's actually not thought of anymore, or over time it was actually changed. The thinking around it was changed, that it's actually not a van der Waals force anymore, but it is dealt with as a separate force on its own. Okay, so tune in for a bit later, okay, if we can get to it in this session, for hydrogen bonding. Okay, hydrogen bonds, they are possibly argued, I think, the second or the strongest intermolecular force that exists. Okay, and we can even give testament to that by acknowledging how long it takes for water to boil at 100 degrees Celsius, which is quite warm. Okay, alcohol, for example, alcohol only evaporates at about 54 degrees Celsius. So alcohol doesn't take that long to evaporate or to change from liquid, aqueous solution, into gas phase. So alcohol boils or evaporates or changes from its liquid state to gas state much quicker than that of water. Okay, so the hydrogen bonds within water are quite strong. Okay. The next one that I want to have a look at, and this is just one way to depict this one, guys. We can also, the molecules can also be drawn like this, negative and a positive, and another one like this coming into contact with each other, positive. Okay, so here we still got that presence of the negative and positive sides of the molecules interacting with each other. Okay, so this side will be bond. So that will be a bond. Okay, they're bonded right there. Cool. That's dipole to dipole, but now we also have a dipole to induced dipole forces. Okay, which we're going to explain now in just a moment. Okay. Okay. So oxygen dissolves in water to a very small extent. Okay, so let's take oxygen for example. Okay, this is important for fish and aquatic life in the ocean. But how is it possible for a non-polar, okay, because O2 is a non-polar molecule, okay, it's non-polar. Let me just do that, yeah. It's a non-polar molecule, okay. How is it possible that a non-polar O2 molecule dissolves in polar H2O molecules? How is that possible is the question that we ask ourselves. Or how is O2, oxygen, able to dissolve in H2O molecules? Because essentially that's what is happening with oxygen in water. Okay, that's why we can't breathe underwater. Okay, the reason is that polar water molecules can induce a dipole in surrounding non-polar molecules. Okay, as the negative side of the polar H2O molecule approaches the non-polar O2 molecules, electrons in the O2 molecule are repelled. All right, and the O2 molecule therefore becomes polar. So let's draw a depiction of that. So here I've got my polar molecule with a positive and negative side. Okay, and this is H2O here because it's polar. And now it is approaching, I'm going to use 3 dots there to show it's approaching, a non-polar molecule with electrons like oxygen has 2 valence electrons. It approaches a non-polar molecule. So we've got polar versus non-polar. Okay, what do you think is going to happen? Let me just draw that line a bit straighter. Come on, here we go. Okay, what do you think is going to happen? We end up with our dipole, which is still our positive and negative polar molecule. Okay, and then we end up with what molecule which was non-polar, such as O2, ending up becoming, and we draw it with a little funny looking S or a incomplete 8 almost, positive and negative over here. This is the depiction of an induced dipole. Okay, it's an induced dipole. So let's read that again. As the negative side, as we see here, of the polar molecule, which is polar H2O, approaches the non-polar oxygen molecule, O2, electrons that's in the oxygen molecule, they are repelled. Okay, and the O2 becomes positive. Oh, sorry, not positive, becomes polar. A dipole has been induced in the otherwise non-polar oxygen molecule. And the H2O and O2 molecules, they can now be attracted to each other. So I'm just going to use these arrows to show attraction. They can now be attraction to each other. This entire process, okay, is called polarization. This entire process of inducing a dipole is called polarization. Okay, that's what it's called. Okay, so in general, the more electrons in a molecule, the more easily the electrons can be polarized because they are far from the positive atomic nucleus. We obviously do remember with regards to molecule structure of the atom from grade 10, we know all the positive protons exist quite close to the nucleus. Right, positive protons and neutrons. So the more electrons that we have there, it's very easy to polarize it because the electrons are quite far away from the positive atomic nucleus, where most of the positive protons are. Let's have a look at an example. Chlorine gas, Cl2 gas, is more soluble in water than oxygen. Okay, because chlorine has more electrons than oxygen. Okay, so chlorine might have 1 electron in its outer shell, but it has 6 other electrons on different energy levels, while oxygen has 2 electrons in its outer shell, valence electrons, but only another 4. So chlorine trumps chlorine gas trumps oxygen gas because it has more electrons. And how did I know that? I just looked at my periodic table. Okay, so only about 0.0004 grams of oxygen will dissolve in 100 grams of water. Okay, so this is just a fun fact to show the fact that oxygen dissolves slowly or to a small extent in water. Okay, because I think if oxygen had to dissolve completely in water, I don't think the fish would be able to function like it does, and we'd have such a exciting marine life at the bottom. Okay, so fun fact, only 0.004 grams of oxygen will dissolve in 100 grams of water. Okay, that's extremely little. That is very, very small. I think I'm even missing a 0 here. Yes, I am. So that's even smaller, 0.0004. That is a number that is very far from 1. It's very far from 1. All right, and it's still quite far from 0 as well. Okay, so 0.0004 grams of oxygen will dissolve in water, 100 grams of water, but 0.7 grams, which is quite close to 1, of Cl2 gas. Okay, I mean both of these are gases. Of Cl2 gas, all right, will dissolve in 100 grams of water. So it just shows you that chlorine is far more easy to induce into a dipole in water than what oxygen is, giving testament to the fact that oxygen actually dissolves to a very small extent in water. And that is my session for today, grade 11s. We will continue going through the rest of the intermolecular forces in the following video. Please keep your eyes peeled for that. Have a fantastic one.